Today we will talk about capacitors with dielectrics, and this is a method of increasing the capacitance of a capacitor by inserting a dielectric slab in the space filling the region between the plates. So a dielectric is a non-conductor or an insulator, for example, and these are examples of these dielectrics. You know many of these examples. Now, what happens, how does a dielectric work? When placed in between the plates of a capacitor, the dielectric reduces the electric field, as we will see, for the reason that we will see now, and therefore it reduces the potential difference for a given charge. So you put a charge, you have a potential difference across the plates of the capacitor generated by this charge, and then when you put a dielectric, this potential difference, the dielectric reduces the electric field and so reduces the potential difference. Okay, and this increases the capacitance, because now this charge, what is the capacitance? It's charge divided by potential. So when the potential drops, the capacitance increases. And the meaning of this is that now you can put more charge until you reach the potential difference that you used to. So the capacitance, okay, of the capacitor increases. That's the idea. Now let's try to, before seeing how dielectrics work, let's look at them a bit closer. There are two types of dielectrics, or many types, but we will consider two types. They are what we call polar dielectrics. We call them dielectric with permanent electric dipole moments among their molecules. Okay, so the molecules forming that insulator have a permanent dipole moment. What does this mean? It means, its example is water. It means that these molecules are already polarized. The charge on them, they are neutral, but the positive charge and negative charge on these molecules are split. Okay, water is an important example of these. Now these are called polar dielectrics. In other words, their molecules are already have permanent dipole, permanently polarized. Now when these dipole moments, when these materials, when these dipoles are placed in an electric field, what happens is that these dipoles, as we have seen in the lecture about dipole in an electric field, they get aligned with the electric field. And so this is the situation that arises. Now there are other types of dielectrics which are non-polar dielectrics. In other words, their molecules are not polarized. So as you can see here, there is no split in electric and in positive and negative charge. However, when you apply an electric field, these dielectrics get split due to the presence of the electric field. Why is this? Because, you know, the negative charge here will be pulled to the left against the electric field. The positive charge will be pushed to the right with the electric field. And so, in this case, they will get split in this manner. Okay? So, the result, more or less, is the same, actually, even in the case of, as is the case in polar dielectrics. You will have a polarization of the molecules. Now, therefore, when you bring this dielectric, consider this slab, and put it in an electric field which is generated among the plates of a capacitor. So this is a capacitor. Before, there is an electric field here. Now we bring this slab and put it here. Due to the polarization that I have just mentioned, at this end, which is facing the upper plate with the positive plate, you will have an induced negative charge density, and you will have an equal and opposite induced charge density, positive charge density, on the end or on the face that is of the slab that is facing the negative charge. This is due to this, you know. So as you can see, it is just this. The electric field is in this direction. So it's the positive plate, the negative plate here. So you will have, this is the charge that will appear at this surface, and this is the negative charge, induced negative charge that will appear at this surface. Inside, there is the polarized molecule. And as a result, we will have actually an induced electric field. So this will act like two charges, two planes of charge. One is positive, the other is negative, okay? And these will produce an electric field in this slab, and this electric field will be against the original electric field. Not equal, of course, it's weaker than that original electric field, but it will be against that electric field. This is called the induced electric field. These charge densities are called the induced charge densities because they are induced only when you put this slab in this electric field, okay? Therefore, due to this induced electric field, the net electric field in the space between the plates drops now. When the net electric field drops, then the potential difference between the plates also drops. Okay? What is the consequence of this for the capacitance? It will increase the capacitance, as I have just mentioned before that. Let's look closer. Yeah. So this is what happens. So E goes to E0 over kappa. V, as a consequence, goes to V0 over kappa. Usually, we usually think of this as actually as a dielectric as changing the permeability of space, because at the end, you know, when you put a dielectric in the space between the two plates is no more free space, and so the permeability of that space is not epsilon naught again, because there is something else. So it's actually, it enhances the permeability of the space by a constant which is multiplying epsilon naught. So you can think of it this way. Why? Because, you know, what is E? E is sigma over epsilon naught. So you can think of epsilon naught going to kappa epsilon, which is kappa epsilon naught. So E becomes sigma over epsilon naught kappa epsilon, which is epsilon naught kappa. So this is why you have a reduction in the intensity of the electric field. It's important to note that here, I mean, you do not, when you want to use these, I mean, it is just either you change epsilon, and so E and V will change automatically, or you change E and then V will change automatically. So you do not just place this in the definition of E and in E, and you put it also in epsilon and so on. You have to be careful when you use this. Now, the dielectric constant of materials is usually a positive number. It is a positive number, and it's greater than 1. Different dielectric materials have different values. So in vacuum, as usual, it is 1 because epsilon is just epsilon 1, epsilon naught. A paper, for example, has a dielectric constant, which is kappa of 3.7. Pyrex glass 5.7. Look, water, because it is a polar molecule, then the induced electric field will be large. And so the reduction in the original electric field will be large. So this is 80. The water has a dielectric constant of 80, which is quite large. Now, let's see in details and quantitatively how does inserting a dielectric in a space, in the space between the plates of the capacitor, in a manner that is in a manner such that it completely fills the space. Okay, so you insert it in a manner that it fills the whole space. So the arguments that the analysis that I'm going to do here are based on this assumption that the dielectric is completely filling the space between the plates of my capacitor. Now, when you work with capacitors, you distinguish two cases actually. One of them is what we call the constant charge condition. The constant charge condition is that happens, or is the condition that emerges when you charge the capacitor fully to a given final charge, and then you disconnect it from the battery. The capacitor is an isolated system. So the charges on the positive and negative plates are now constant. There is no source or sinks of charge on that. Okay? This happens when you charge the capacitor, disconnect it from the battery, and it is isolated. Now, under this condition, assume we have a capacitor that has been charged. Okay? So there's a given charge Q naught on it. Naught here means before you insert the dielectric, and therefore there is a potential difference V naught across this capacitor. There is also there is an electric field E naught across the plates. Now you insert the dielectric. Once you insert the dielectric, well, the electric field becomes E0 over kappa. Okay, so it drops. So the new electric field E is equal E0 over kappa, just what we have said here. And since what is the voltage? The voltage or the potential is just E times D. So the new voltage will drop also by kappa. So the new voltage now, the new potential difference across the plates after you insert this, drops by factor of kappa. Okay, this is what is trying to do. This is a voltmeter. It was this, and becomes less now. And therefore, what happens to the capacitance? The capacitance is all the time, regardless of anything, is the ratio of the charge on the capacitor divided by the potential difference across the plates generated by this charge. Since the charge remains the same, this potential drops, then actually you get this equation. So it's kappa multiplied by Q naught V naught. What's Q naught over V naught? Q naught and V naught are the charge and the potential before you insert the dielectric. Therefore, the new C, the new capacitance, is equal to the, after the dielectric is inserted, is equal to the capacitance before the dielectric. In other words, in free space, when the space between the capacitor is just free space. There is nothing or air. This is, the note refers to that situation. So C becomes kappa multiplied by this. Since kappa is a positive constant greater than 1, then this actually enhances the capacitance. It increases the capacitance by a factor of kappa. This is a general result. Whenever you have a capacitor and you have a dielectric slab inserted, completely filling the space between the plates, then the capacitance increases by a factor of kappa, regardless of any other consideration. Okay, so this is a general result in this case, and this is something you can understand. We have introduced that. Now we have two checkpoints here to test your understanding of what we have just said, and they need a bit of thought, so please do these before you proceed. Now we look at the second situation. In this case, the constant potential condition of a capacitor. A constant potential condition for a capacitor is when you have the capacitor all the time connected to the battery. Okay? The meaning of this is that the potential difference across the capacitor is always constant. As long as your capacitor is connected to the battery, your potential difference will always be constant. The reason is very simple, because you know what happens when you charge a capacitor, the charge starts accumulating here and negative charge accumulates here. Now there is a potential, a constant potential difference between the plates of the battery. It's constant. Okay, it's what you write, you see on the battery, 12 volts and so on. What does it mean? There is a potential difference of 12 volts, for example, between this and this. Now, how much charge will accumulate on this? Okay, to what extent this charge will continue accumulating? Actually, it will continue until these two are at the same potential. Okay, because these are connected together, then they act as a single conductor, and they will reach equilibrium when the potential, not the charge, the potential here of this plate and the potential of this plate is the same, and the potential of this plate and this terminal are the same. And therefore, in this case, the potential difference across the battery is the same as the potential difference across the capacitor. This is how things happen. As long as you are the capacitor is still connected to the battery, whatever you do here, the potential, charge will rearrange itself so that you will always have the potential difference across the capacitor always equal the potential difference across the battery, as long as the battery is still connected to the capacitor. Whatever you do for the capacitor, that situation will always be maintained, okay, the potential difference. This is important. So now we have this capacitor. There is a V naught now here across its terminals. This V naught will be sustained. Now you insert a dielectric constant here, the dielectric slab here, filling the whole space between them. Now what will happen in this case? This will try to reduce the electric field. The potential across this will momentarily be reduced. But come on, this means that the potential of this will be less than the potential of this immediately once you or momentarily once you insert the slab. Therefore now, how you can increase the potential of this? More charge will come and accumulate here, and the same applies here. More charge will come and accumulate here. So this will continue until this and this are again at the same potential. The result will be an increase in the charge accumulated on this plate and in this plate, of course. Okay, so when you insert a dielectric to between the plates of a capacitor, when this capacitor connected to the while the capacitor is connected to the battery, the momentary drop in the potential of this plate and this plate between these plates, and so this plate with respect to this will lead to a charge being driven from the battery to this plate until these two are the same potential and these are the same potential, and this leads to an increase of the charge on the plates of the capacitor. Okay, so this is what the dielectric slab does in this case. Now, what is the new charge? How is the new charge now related to the old charge? Okay, the charge is always CV from the definition of the relation between Q, V, and C, but the new C now is kappa C naught. Okay, so you can think of them, because V remains the same V naught, it must remain after the charge has been driven here. Then the C naught V naught is the old charge, Q naught, charge before you insert the capacitor. So the new charge is kappa multiplied by Q naught. So actually the charge increases by a factor equal to the dielectric constant. Okay, the charge does this increase in charge is necessary so that the potential difference across the capacitor remains V naught, which is the original one, which is the potential across the battery. Now, these are also two checkpoints that you need to consider before you proceed. Now I will work out a numerical example, and in this example we start with a parallel plate capacitor with the space filled completely with a dielectric material which has dielectric constant 4, and while this dielectric slab is there, it's connected to 100 volt battery and it's fully charged. So after it's fully charged, you disconnect the battery. Okay. The plates are 4 meters square. The area of each plate is 4 meters square, so it's a huge actually capacitor, and the separation is very small. It's just 4 millimeters. Okay, this is not a practical capacitor anyway. We are requested to find some quantities like the capacitance, the charge, electric field, energy before, when the dielectric is there, and then after we remove the dielectric, when it is disconnected now from the battery, we are requested to find what are these values. And in view of these values, we are requested to find what is the work done in order to remove this dielectric from the between the plates. Okay, we will do this in details now. So we will now see how we can solve this example, and what we are given is, let's plot the situation. This is the positive terminal, this is the battery, and this is the negative terminal. Now we start with a situation when this is the dielectric slab, and the dielectric slab is completely filling the space between the capacitors. Now what we are given is that the potential of the battery, which is, I call it V, no, it's not V naught here, sorry, it's just V. The potential or the voltage of the battery is 100 volts. The area of each of the plates is 4 meters square, and the separation of the plates is 4 millimeters, and kappa is equal to 4. So this is the situation I have. Now, under these conditions, I am requested to find what is the capacitance of the capacitor, what is the charge on the capacitor, what is the electric field in the in this region with the slab in, and what is the energy. Now these are easy things to find. So I will start with Q, and Q is equal to C times V. Okay, and C, as I know, is just K kappa C naught multiplied by V. C naught is the capacitance of the parallel plate capacitor in the absence of the dielectric, okay, when this area is filled with air. So now everything is, what is C naught? C naught is for a parallel plate capacitor epsilon naught A over D. And now, so therefore, this expression becomes kappa epsilon naught A V over D. And what remains is to substitute these numerical values and work it out. Now, in this example, just for computational simplicity, I will express all the results in terms of epsilon naught. So I leave the answer in terms of epsilon naught. So I substitute here. Kappa is 4, A is 4 also, and V is 100. D is 4 times 10 to the power minus 3, and you write this as epsilon naught, and therefore you get this as, this cancels this, and this goes up, so it becomes 5. So the answer is 4 epsilon naught times 10 to the power 5 coulombs. Okay, so this is my charge. This is the charge on the capacitor. Of course, epsilon naught is 8.82 times 10 to the power minus 12. So here actually you have 10 to minus 12. So this quantity, it seems 10 to 5, it's actually of the order of like 10 to minus 7. So it's in microcoulombs, okay? So the charge is small. But, since I'm keeping this in terms of epsilon naught, this is why I have 10 to 5 here. So keep this in mind. So this is the first thing. What is Q? Now what is the electric field? The electric field is what? It is actually equals V over D. Because V is equal E times D, okay? Now the battery here is maintaining a potential difference of V, and I know the separation, so it's easy to find the electric field. You substitute, this is 100, and this is equal 4 times 10 to the power minus 3. 100 over 4 is just 25, so it's 25 times 10 to the power 5 volts per meter. So electric field is high, actually, in this case. And this is the electric field in the region here in the presence of the dielectric, when the dielectric is existing. So we have found Q, we have found E. Of course, epsilon, kappa is, or the capacitance is just, kappa multiplied by C naught, which is just, this is your this is C naught, and this is kappa. So this is your new capacitance, of course. This is what I have used for my new capacitance. Now, I want to find the energy. What is the energy? No, we know what is the energy. Energy has 3 equivalent relations: Q square over 2C, or 1/2 QV, or you can, the other relation, and we have eliminated here C. You can eliminate, for example, Q from here. So Q is equal CV, so it's 1/2 CV square. They are all equivalent, and you can use whichever is convenient for you. Now I have Q already, and I know V, so I will use this. So this is equal 1/2 multiplied. What is Q that I have found? It is 4 epsilon naught times 10 to the power 5, and V is 100. Okay, so it is actually 4 divided by 2 is 2. So 2 times 100 is 200 times to the power 5. So it becomes 200 epsilon naught times 10 to the power 5, which becomes actually 2 epsilon times 10 to the power 7 joules. Again, keep in mind that epsilon naught is of the order of 10 to minus 12. So this quantity is actually of the order of 10 to minus 5 joules. So it's small. Okay. So this is the energy stored in the capacitor when the dielectric is filling the space between them. Now, the second, what happens next is I remove this dielectric slab. Okay. Now, what will happen in this case? Of course, let me first understand or analyze whether this is a constant charge or a constant potential. In the problem, it says that you charge, you disconnect from the battery, okay? And this is what you have. Now, when this is disconnected, you remove the slab. So the slab is removed when this is disconnected from the battery. And in other words, the capacitor is isolated. So this is a constant charge condition. So the charge here doesn't change. It remains as it is. So now I have the situation here where Q naught is equal Q, the Q that I have found. But what will happen in this case? What will happen to other quantities? So this is a constant charge situation. Well, since the when you had the slab, I had an electric field reducing the original electric field. Therefore, when I remove it, that induced opposite electric field will disappear, and therefore the electric field will get enhanced. The electric field will increase. And as a consequence, the potential difference will increase. Okay? So this is what I know. Let me try to see how I can find this. It's quite easy, by the way, to find these. First of all, so when dielectric is removed, I know now Q naught is equal Q, and it is this quantity that I have found, which is 4 epsilon naught times 10 to the power 5 coulombs. Okay, and C naught now is just epsilon naught A over D, which is what I have here. Now, I want to find what is the new E and what is the new D. Now, actually, I'm asking about E naught, because the new E here in this case means the E after the dielectric slab has been removed. But this is what we used to call E naught. What is E naught? Well, I know that E is equal E naught over kappa, and therefore E naught is equal kappa E. So it is enhanced, and this is what I expect. I mean, the electric field will go up, as I have just said. And what was the original electric field? The electric field was 25 times 10 to the power 5. Now you multiply it by 4, because kappa is equal to 4. So this is equal 4 times 25 times 10 to the power 5. And this quantity is equal, it is 100, and so it becomes 1 times 10 to the power 7 volts per meter. So this is your electric field. It's 4 times larger than the electric field in the presence of the dielectric. Now, what about the potential? V in this case, or V naught? Well, V naught, you can think of it as equal E naught D. Okay? Or, simply, you can say that in this case, V naught over kappa was equal to V, so V naught is equal kappa V, which is 4 times V, and this will be 4 times 100, so it will be 400 volts. So, I mean, you can definitely find it using this expression, but because you know what is V already, you can immediately find it from here. So it's just 4 times V, 100 is 400 volts. So voltage also increases because the electric field has increased. So that makes quite sense. Now, what about the energy now, which we call it U naught? What is U naught? What is my new potential energy? Well, it is just this expression with these quantities replaced by the noted quantities. So it will be Q naught square over 2 C naught square, 1/2 Q naught V naught, but Q naught is the same as Q, so it doesn't make difference, or C naught V square. But I will also use this because I already have these expressions. So U naught is equal 1/2 Q naught V naught. Q naught is the same as Q, okay, which is just above. So it's straightforward to substitute here. So 1/2 times, what's Q naught in this case? Q naught is 4 epsilon naught times 10 to the power 5. And what is V naught? V naught is 400 now. Okay, so again, this is 1, this is 2, and this becomes 2 epsilon naught times, so 2 times 400, which is 8. So it is 8 epsilon naught times 10 to the power 7 joules. Okay. Now, evidently, if you check this and compare it to this, you can write from here. This is equal 1/2. You keep Q naught as it is, and this is 4V. So it's equal 1/2. Sorry. It's equal 4 times 1/2 Q, because Q naught is the same as Q, QV. Okay? So it's 4 times this quantity, and exactly this is what you get. Because if you multiply this by 4, you get this expression. Okay? So this is equal 4U. So what has happened is that when you remove the dielectric, the potential, as you remove the dielectric, the potential energy has increased. So when you remove the dielectric, the potential energy of the system has increased. And this leads us to the last expression, which is what is W external done when you remove the dielectric. W external is what? Is delta U. And in our case, delta U is U final minus U initial. I mean, delta here is the latest minus the earliest. What is the latest one? It is U naught. And the earlier is U. Okay? U naught. So it's 4U minus U, so it's 3U. This becomes 4U minus U, which is equal 3U. And what is U in this case? This was equal U, so it becomes, and this is equal 6 epsilon naught times 10 to the power 7 joules. So the work here done by the external force to remove the dielectric actually is a positive work, So that external force that you have used in order to remove the dielectric, it has increased the potential energy of the system as you remove the dielectric slab. Now, of course, this leads to the question, which is a bit question that you need to think about it. As you remove this slab by this external force, will the dielectric, will the capacitor be pulling in the slab as you remove it, or it will be just pushing it out? It will be pushing it out. Okay? So you remove the slab from rest, you move it very slowly, and so you don't change its kinetic energy. So W external is delta U. So when doing so, will the capacitor be pulling this slab in while you are removing it, or it will be just pulling it out, pushing it out? Okay? Try to think of this answer, and the answer, of course, lies in what is the delta U. Is it positive or negative?